All right. So hello, everyone. Welcome to this PhD defense presentation. Thank you for being able to be there online, especially for those whose current local time is not ideal. And thanks again to the jury for the time and efforts they put in reviewing this thesis. So the title of our work and of this presentation is Automatic Curriculum Learning for Developmental Machine Learners. In other words, it is about studying how to design and use teacher algorithms to organize the training schedule of embodied machine learning students. So the presentation will last around 45 minutes, and I'll start by some background on making interactive agents, mainly through the reinforcement learning perspective. And I'll then describe automatic curriculum learning, ACL for short, which is an important set of tools towards training robust interactive agents. And then I'll focus on 3 computational experiments featured in the thesis. The first 2 are direct contributions to the ACL field, and the last one focuses on a parallel and complementary perspective on how to build proficient agents. And I'll close this presentation with a short discussion on related recent works and future prospects. So how do we create an artificial agent able to interact and learn efficiently within complex environments? That's a long-standing question, perhaps the foundational question of the reinforcement learning field. So then what is reinforcement learning? RL works are interested in making interactive learning agents able to learn behavior policies using an artificial form of trial and error learning. The objective of the policy is to find the right action to perform given the current observed state of the environment, such that reward collection is maximized. And the reward is defined by the experimenter to guide this learning process. And since 2013 and the DeepQ network algorithm, we are more and more talking about deep reinforcement learning, that is RL algorithms featuring multi-layered neural networks able to deal with high-dimensional action or state spaces. For example, in this work, they show that their DeepQ network architecture is able to play Atari games at human-level performance only by receiving pixels as observations and the game score as a reward. And since then, DeepRL algorithms have repeatedly proven to be powerful learning systems. However, the highly efficient policies learned by classical DeepRL methods suffer a very important limitation. They tend to overfit their policy to their training environment, such that minor environment variations at test time can drastically reduce their performances. And this observation is not new, and an increasing number of works is studying how to learn robust policies that would be able to operate efficiently in multiple related problems, potentially never seen in training. And this is what is often called the generalization problem. And from a high-level perspective, this has been approached in 2 ways. First, many works focused on building more efficient learning algorithms. For example, by adding regularization mechanisms to complement the reward optimization process. And one classical method coming from supervised learning is to enforce simplicity in the learned parameters of the agent, such that its behavior will be more general and will better transfer to unseen scenarios. Another approach is to add architectural biases in the learning agents, such that they can better cope with variations between training and testing. For example, in this work from Tang and Ha, they propose a DeepRL architecture that is robust to observation permutations. And another existing perspective towards building better agents, which we decided to further study during this thesis, is to focus on improving the training environments. So improving how a given DeepRL algorithm is trained. And so if the objective is to learn robust multi-purpose policies, then a natural approach is to train the agent not on a single deterministic scenario, but on a diversity of environments, such that it must learn to deal with many different situations. And given this, one typical follow-up from the DeepQ network paper on Atari games is to train not on a single Atari game, but on multiple games at once. This can be quite efficient. However, the diversity is still limited. There is a discrete number of deterministic environments. So it is possible for a DeepRL agent to learn a set of deterministic policies that will be optimal, but will still lack robustness if tested on modified environments. So it's not an ideal route towards more general agents. However, an increasingly popular approach to generate a high diversity of training environments is to leverage procedural content generation techniques. First used as a way to generate video game content in the industry, procedural content generation, PCG for short, proved to be quite efficient to generate diverse training sets composed of a potentially infinite number of unique environments. And a related concept, which can be seen as a form of PCG, is domain randomization, which comes from the robotics field. For example, in this paper from Tobin and colleagues, authors show that training on a diversity of simulated environments whose physical and visual characteristics are randomly drawn from a distribution allows to learn a policy robust enough to be directly used in the real world without fine-tuning. But if the procedural content generation does allow to produce a huge amount of diverse environments, which helps for generalization, it does bring an additional problem: how to deal with this training diversity. For example, if considering complex generative systems, a lot of produced environments might end up being unfeasible, or at least initially unfeasible for a given learner. And so randomly proposing environments for training does not seem like an optimal choice. And this question is quite central to our work, and the answer we've tried to formulate for it is about curriculum learning. Indeed, if we assume access to the PCG system, it seems like a learning agent could benefit from a teacher algorithm providing a structured training schedule compared to random procedural generation. So before discussing the advantages of curriculum learning for modern DRL challenges, let's focus on curriculum learning itself. So the concept of curriculum learning in reinforcement learning is an old story. For example, in this 1985 Ishkai article, Selfridge and colleagues used what they called learning schemes, so a curriculum, to train a pole balancing controller. And here the objective was not to foster generalization, but rather to enable the sample efficient learning of a complex task by learning on simpler variants first. And so one issue with this classical form of curriculum learning, where a set of environments are sequenced by hand, is that it requires a domain expert to arrange the curriculum, which takes time and effort. And it does not easily transfer to new learning scenarios. And so answering these concerns is about seeking to design automatic curriculum learning methods. And in terms of ACL algorithms, many interesting ideas emerge from the developmental robotics branch of AI, which seeks to understand and test human learning theories by modeling them into autonomous and embodied learning agents. More precisely, developmental roboticists have long been interested in building computational models of humans' intrinsic motivation, which has been identified in developmental psychology as a main driver for humans' cognitive complexity. So here, intrinsic motivation models can be seen as a specific form of automatic curriculum learning, which is not about coupling a teacher algorithm sampling tasks to a given learner, but rather to enable agents to autonomously shape their learning journey. And from this literature emerged a particularly efficient form of intrinsic motivation system, which is learning progress. For example, work done in the team showed that by organizing self-exploration using learning progress allowed to learn complex nested tool use behaviors jointly and efficiently. Here, this robot manages to learn in a few hours that to play with the tennis ball in front of him, it needs to grab the right joystick to control the robotic toy in front of him and use it to push the tennis ball to a self-selected location. So, learning progress is a simple concept. It can be defined as the derivative of competence. The idea is that to maximize the efficiency of your learning session, you should focus on objects or situations for which you are improving most, so that you do not waste time on trivial or unfeasible problems. And to better understand this, we can look at these two illustrations of an hypothetical agent using learning progress-based intrinsic rewards to improve over 5 imaginary tasks. Here, as in the robotic experiment I just mentioned, tasks have different difficulties. For example, the blue one is easy. It would be similar to exploring the arm positions in the robotic experiment. The green one is hard, as when trying to move the tennis ball by using the right joystick. And some tasks are not learnable, like the purple or red tasks. So the right figure illustrates the schematic task selection preference of the agent across training. And you can see that if the agent uses the derivative of competence to choose which task to focus on, it is able to efficiently and autonomously allocate its training time into a coherent learning curriculum. For instance, the agent initially focuses its training on the blue task, for which high learning progress is initially experienced, while marginally training on other tasks to maintain exploration. And after reaching a performance plateau on the blue task, so a low learning progress situation, our learner shifts its focus towards more promising tasks while avoiding wasting time on unlearnable ones. And so, by the way, the first step in our work was to study these methods from developmental robotics And as such, we designed a complex multi-object Minecraft scene to conduct experiments complementary to those done with the robotic playground, which we recently integrated into a common publication about intrinsically motivated agents. So the learned behaviors of these agents are quite impressive. However, they have one strong limitation. They rely on growing a population of expert policies, with each of them dedicated to perform a single action sequence. So here again comes the problem of robustness. If you move the right joystick 10 centimeters from its location at training time, performance collapses. And so an important goal for this thesis was to leverage this literature about building intrinsic motivation systems, especially work on learning progress, and turn it into external ACL teacher algorithms for DRL students. So now let's shift back to modern DRL concerns and look at what was the state of ACL for DRL at this stage in the thesis. So first, we can briefly go over the setup. We consider a DRL student learning a policy pi throughout interactions in tasks tau defined as episodic Markov decision processes. We then have the ACL algorithm, which is learning a task selection function D, which outputs a new task at each training step based on the student's history of interaction. And these tasks are selected from a predefined discrete task set or continuous task space. And we assume that training time is finite and is composed of E task sampling steps. Given this, the objective for the teacher is to improve the training efficiency and asymptotic test performances of the student compared to when using a random curriculum. And more precisely, the objective for the ACL algorithm is to maximize the post-training performance of the student over the target task space or task set. And in practice, because this objective is hard to optimize for directly, current ACL approaches use surrogate objectives, like learning progress, for example. And that, all right, that's it for the formalization. So now let's go over some literature. So while in the process of writing a survey paper on ACL for DRL, we propose to classify ACL works using 3 different viewpoints. First, we sort current works based on the main motivation that led them to use ACL. Was it to foster generalization or maybe to solve a single very hard task? And then we look at which aspect of the learning scenario is controlled by the ACL algorithm. In practice, it means which part of the task MDPs are being adapted throughout training. And finally, we look at what is the nature of the optimization objective used by each ACL approach. Is it learning progress or maybe diversity? And given the 3 axes, we surveyed many ACL works and compiled our analysis into a big table. And for time's sake, in this presentation, we briefly overview the last 2 proposed axes. So classical automatic curriculum learning is about controlling parameters of the tasks being proposed to the learner. More precisely, this control can be applied over all MDP components. For instance, with the initial state distribution. So here, using ACL is about choosing from which state to start interacting in a given MDP, which can have strong impacts on task difficulty, especially for complex robotic manipulation scenarios. ACL can also be applied to control which goals to propose to a DRL learner. This is, for instance, what is performed in the Curious architecture from Kola and colleagues, where they control which action should be tried on which object of the scene for each new episode. And ACL has also been used to complement the reward function of a given task's MDP by adding intrinsic rewards, which is often used to ease learning in hard exploration scenarios. And as we discussed earlier, a growing body of research is also looking at training on a diversity of related environments. And we are not the only ones thinking that ACL can be useful in that realm. And finally, ACL can be applied to control the transition function of a given MDP, which often translates to control opponent generation, as in self-play works like the famous AlphaGo agent from DeepMind. In the end, every aspects of the MDP can be leveraged by ACL algorithms to adapt what is proposed for interaction to the learner. So the next perspective is to look at which surrogate objectives have been considered in the literature. And the real question here might be how to detect that a task is interesting and worth training on. So the first natural option is to set a reward interval corresponding to tasks of intermediate difficulty, as defined by an expert, and to focus sampling on tasks for which the agent's return falls in this range. This approach does require expert knowledge to set it up, but it can work very well. A potential issue, however, is that you can get stuck in sampling tasks of intermediate difficulty for which the agent cannot improve, which is a waste of learning time. And in a sense, we see learning progress as an interesting alternative to intermediate difficulty methods. Using learning progress does not require a specific intermediate reward range. It just needs to control empirical performances and analyze their evolution with respect to each task. However, at this stage in time, only a few learning progress-based ACL approaches were tested on DRL agents, and only to organize training over a discrete set of tasks. And so a core objective of the thesis was to show that it is possible to apply learning progress to control continuous parameters encoding the procedural generation of environments. To briefly close this slide, there are many other surrogate objectives for ACL, like the adversarial reward maximization strategy used in self-play, the optimization of surprise or diversity, often used for exploration bonus generation, and others like optimizing for reward or energy. So now let's talk in more details about our first experimental contribution to the ACL field, which is the ALP-GMM teacher. So in this work, we consider the following problem. Given a continuous space of procedurally generated tasks, in our case, a continuous set of walking tracks varying by their obstacle layout, how do we train a DRL student to be as good as possible over the space and learn a robust locomotion policy? As we discussed, if the parameters encoding the procedural generation are controllable, an interesting approach is to leverage a teacher algorithm to sample tasks and guide the learning process of the student by focusing on relevant task subspaces throughout training. So how do we create this ACL algorithm? And importantly, to avoid overfitting our method to a specific teaching problem, we wondered how could we perform ACL without relying on knowing the initial abilities of the learner. As such, we decided to consider multiple learners, varying by the morphology of the walker they control. And we propose to frame our approach as a black box teaching problem, in which the teacher must sample and propose tasks to its student only based on observing the episodic rewards that the student obtain on each task. And importantly, to be able to deal with students of varying abilities and to deal with complex procedural task spaces, we cannot assume that the task space is entirely relevant and feasible for each student. And anyway, in the long run, if we start to consider very complex procedural spaces like 3D open worlds such as Minecraft, we cannot assume access to a clean and simple task space. And so we must assume that it could contain unfeasible subspaces, irrelevant dimensions, and nonlinear difficulty gradients. And so with this in mind, we propose the ALP-GMM algorithm, which stands for Absolute Learning Progress, Gaussian Mixture Model. Let's unpack these terms. ALP-GMM uses a learning progress-based heuristic to figure out interesting tasks to focus on. The challenge here is that there isn't 4 or 5 tasks on which you can easily log your competence improvement and use the derivative of this curve as your empirical learning progress signal, but there is an infinity of tasks which you will potentially never train on twice. And as such, our approach is based on exploring the task space, proposing tasks to the student, and computing noisy per task learning progress estimates that are then aggregated into local learning progress estimates to figure out interesting task subspaces on which to focus sampling. And once these task subspaces are identified, then you recover a scenario similar to the discrete task set case. And you can apply a bandit algorithm to organize task sampling, or rather task distribution sampling, which basically means that you sample in task subspaces proportionally to their estimated learning progress value. And so we use the absolute value of learning progress to be able to detect negative learning progress, so learning regress. DRL agents have a tendency to erase previously learned behaviors while learning new ones. And so by tracking absolute learning progress, we can shift task sampling back to previously mastered subspaces if they are starting to be forgotten. And finally, to efficiently detect and fit complex task subspaces, we rely on fitting Gaussian mixture models using our database of proposed tasks and associated absolute learning progress estimates. So each Gaussian becomes an arm of the multi-arm bandit. And so to recap, once this Gaussian mixture model is fitted, with each Gaussian associated with a learning progress value, ALP-GMM is able to sample a new task, or rather a new parameter vector, that will encode the procedural generation of a task. And then the DRL student is challenged with this task for an episode, and by the end of it, LPGMM observes the student's episodic return, so the sum of rewards obtained during the episode. And this episodic return is used to compute a noisy absolute learning progress estimate. I won't go into details about that, but I have a few supplementary slides about it if you're interested. And finally, the new task and associated absolute learning progress measure is stored into a short buffer, which is periodically used to refit the Gaussian mixture model and adapt to the evolving performances of the learner. All right, that's it for the method. So in our experiments done on the procedural locomotion environments I mentioned earlier, we test LPGMM paired with a soft actor critic student, a recent DRL architecture, and show that LPGMM is better able to maximize the abilities of its student than a random curriculum, previous learning progress-based algorithms coming from developmental robotics, and occasionally even expert design curricula. And we also show these results hold in a more complex 12-dimensional task space featuring irrelevant dimensions and nonlinear difficulty gradients. So here are post-training examples of a median LPGMM run and a median random run. So to sum it up, with limited information, LPGMM is able to catalyze the learning of its DRL students better than using random task sampling techniques, enabling to learn robust locomotion policies. So this concludes the presentation of our first experimental contribution. So now let's go over the next one, which is the Teach My Agent benchmark. So this work originates from a simple observation we made while writing our survey article. The automatic curriculum learning field, or at least its subpart interested in building teachers dealing with continuous task spaces, is quite a mess. What we mean is that many different works are being studied in parallel, which is good news for the field. It is active and growing, but the current lack of comparative studies between each approach makes it hard to understand their relative advantages. This is problematic for researchers, but even if you're not interested in doing ACL research, but you're just looking for a teacher to plug in your learning pipeline, then it's also hard to understand which approach is best for you. Each paper considers only a subset of existing methods, and they test them on their environment while assuming different expert knowledge settings, which makes it very hard to compare approaches from paper to paper. This is not an ideal situation, given how benchmarks can catalyze research, for example, how the Atari benchmark helped the DRL field to develop new approaches and improve upon the vanilla DeepQ network I mentioned earlier. So it seems like it would be interesting to have something similar for ACL algorithms. But although there are many DRL benchmarks, we don't have a single equivalent for teachers. And so in this work, we decided to try to create a standardized testbed for ACL algorithms. And we named it Teach My Agent. This benchmark features many components that I'll overview briefly. Importantly, it contains multiple implementations of recent ACL algorithms. And we assembled this set from open source codes that we adapted to our common API, but we also re-implemented some algorithms from scratch when code was not available. And to compare these teachers equally, they need to be tested on the same students. So Teach My Agent also contains two state-of-the-art DRL students. The soft actor critic learner we use in our work around LPGMM, but we also added another popular method called proximal policy optimization. And so Teach My Agent is also composed of two parametric locomotion environments using procedural content generation. First, we reuse our Walker environment named Stump Tracks, which has a two-dimensional parametric space to generate obstacle layouts. And we use it as a simple teaching setup that is convenient to analyze specific teaching challenges. And then to provide a more complex testbed, we designed a parametric parcours environment. So the environment you see on the screen is just one point in our 6-dimensional parcours space. 3 of these dimensions are parameters used to seed a compositional pattern producing network, which enables to generate complex ground and ceiling layouts. And the last parameters control the height and spacing of graspable creepers in the ceiling and the water level in the parcours. And so the objective here was to create a rich task space that will have a completely different difficulty profile depending on the abilities of the considered students. And so speaking of students, to increase the diversity of teaching problems, we decided to create multiple embodiments. And this is especially relevant for parkour environments that can be solved with many different locomotion strategies. So first, we added walker morphologies, including our previous bipedal and quadrupedal agents from LPGMM, but we also created new bodies like this spider on the top right image. We then added morphologies specific to the parkour environment. So agents able to climb and agents able to swim. And so in the end, the cross product of available DRL algorithms, PCG environments, and agent morphologies gives you a large set of teaching problems to thoroughly compare ACL algorithms. And to organize this comparative study, we defined and described two forms of experiments. So first, we try to identify a set of teaching challenges, for example, dealing with students that forget, dealing with task spaces that are predominantly unfeasible or trivial. And then we used variants of the stump track task space to construct tests requiring specific teaching skills. And then we also defined a global performance test using the parametric parkour environment, since it already features multiple core ACL challenges. And this gives you the full TeachMyAgent testbed. So we then used TeachMyAgent and performed a large-scale study by testing all our ACL algorithms with our two types of experiments. So first, we performed the skill-specific experiments I mentioned, allowing to create this kind of radar plot. Each branch corresponds to a specific teaching challenge. And for each of them, we logged the performance of each teacher relative to our random curriculum baseline. And we add a star if the teacher significantly outperforms the random curriculum baseline by the end of training. Importantly, we repeat all these experiments with 3 different expert knowledge setups. And here I'm showing the high expert knowledge setup, where we provided to each condition, if needed, a reward range corresponding to tasks of intermediate difficulty, an initial distribution of easy tasks, and a target task distribution. And so given all this information, it's not surprising that most approaches outperform the random curriculum. However, when we reduce the amount of available expert knowledge, so when you give the intermediate reward range, but you no longer assume that you know where to start and where to go in the task space, then performance starts to degrade for methods who rely on it. And without any expert knowledge, you are no longer able to run some approaches. So we also run our global performance analysis on the parkour environment. And here, in terms of expert knowledge, we only provide the intermediate reward range, so the low expert knowledge setup, since the task space is quite complex and its difficulty depends on the particular morphology of the student that is being trained. I don't have time to get more into details about the results, but an interesting observation that comes out of both these experiments is that ACL approaches that do not rely on expert knowledge, like LPGMM, are quite competitive. And so that was TeachMyAgent, an open source benchmark for teacher algorithms. Our code is available at this link, along with a detailed documentation and scripts to reproduce our experiments. And we also released the full results of our experiments, such that new users will only have to run their new ACL algorithm to compare it with all of the ones we already analyzed, without additional computational cost. So note that it is only version 1.0 of TeachMyAgent. We would like to increase the diversity of considered environments. So far, it's essentially focused on locomotion. We could also add more recent ACL methods to the existing set. So to close this part of the presentation, I'd like to mention that using the parkour environment, we created an interactive web demonstration that we presented at a science fair in Bordeaux, Cap Science, to illustrate the challenges of deep reinforcement learning and automatic curriculum learning. And among other things, this demonstration allows users to draw their own parkour track and use it to challenge pre-trained DRL agents from our TeachMyAgent experimental campaign. And so the demonstration was written in JavaScript and runs on the browser of the user. It's still available at this link. And so beyond the pedagogical and fun aspect of the demo, an interesting research use case that we just tried but did not study thoroughly yet is to use this interactive tool to test to which extent our agents are able to perform out of distribution generalization. For example, here we found interesting result when challenging walkers with big jumps big jumps on the left, and on the right side, we show multiple climbers competing to grab movable creepers, although we never train them with movable creepers, and we use fixed creepers in the experiments. And we also never train them with competing opponents able to move these creepers. All right, so that's it for the demo. Now let's move on to our last contribution, which is the social AI project. Compared to our previous studies around ACL, this work can be seen as a parallel perspective towards building robust machine learners. More precisely, we see it as a complementary project. And before going into details about what we've done, let's clarify this link. So this quest towards making agents able to generalize can be seen as a proxy towards a longer-term objective in machine learning. We want human-like AI. I mean, autonomous agents able to interact with us efficiently outside of the lab. And surely, these agents will need to have robust locomotion and object manipulation skills. But a key feature is that to interact with us fluently, they will need social skills. So to get there, we need to train them in social environments. And here is the link with our previous works. As I mentioned earlier, this thesis focuses on designing better environments to train better agents. And this can be done by controlling the evolution of a given environment with automatic curriculum learning. But another perspective is to consider the nature itself of the environment. And we argue here it needs to be social. And an interesting theory towards this, coming from developmental psychology, is that for humans, exposure to sociocultural environments shape our cognition, and not the opposite. In other words, we are smart because we are social. This importance of social interactions when creating learning machines motivated entire research fields, such as in a human-robot interaction or in the social robotics branch of developmental robotics. But where are our social DRL agents? If social skills are so important both as tools to refine cognition and as an application area in itself, why aren't they at the center of attention in the field? We are not the first ones to raise these kind of questions. And so there is now a growing number of works interested in embodied social interactions in DRL. So let's have a quick look at this literature. More precisely, let's focus on works featuring embodied agents able to use some form of language. So the first relevant subfield concerns all works leveraging text-based games to study DRL agents. So in text-based games, you're dropped in a textual world, usually separated into multiple rooms like the kitchen, the garden, etc. And you can interact and explore this world by inputting textual actions. Go south, go north, open mailbox. And as observations, you receive textual descriptions of the room, of the result of your actions, and also potential utterances from NPCs that might be in the room. So NPC, non-player character, another agent. So here the embodiment of the agent is virtual. So for example, some authors propose the light environment, which is a text-based environment featuring scripted NPCs built from crowdsourcing. And another relevant work is a text world project, which released a procedural text game generator, useful to study how agents can generalize in text-based scenarios. All right, then another relevant subfield are works studying language condition agents. So they are looking at how it is possible to train DRL agents able to follow goals formulated with natural language. And within this literature, an interesting setup is to consider embodied question answering agents, EQA. So agents that are dropped in a physical world and they are given a question like what color is the car, as in this example, and they must then navigate in their world to gather information so that they are able to answer the question with natural language. So text worlds, embodied question answering, and the last relevant set I'd like to mention is multi-agent emergent communication, which gather works considering the training of multiple learners able to communicate with each other to achieve cooperative tasks. It is named emergent because the idea is to study how language conventions can emerge. For example, how in an environment, agents must learn to negotiate communication symbols with each other using language such that they can share information efficiently. So here are the three main lines of works currently studying social skills in DRL. And given this literature, an important observation we try to put forward in this work is that the diversity and complexity of currently studied social interaction is quite limited. For example, in text world, the virtual embodiment prevents any form of physical exploration and nonverbal communication. In embodied question answering, the agent is not among social peers and is stuck into a rigid interaction protocol where it receives the question, navigates in the environment, and uses language to produce an answer. And so far, probably due to the complexity of multi-agent training, multi-agent emergent communication only studies simple environments with simplistic languages, usually about outputting a single symbol per step. Also, they consider the problem of negotiating social conventions among learners. However, an important setting is to have a single learning agent, which must enter an already existing social world and learn its existing conventions. And so given this perspective, we set ourselves the goal trying to create a set of environments named social AI, which will feature complex and diverse forms of embodied social interactions. We are thinking, for example, about multi-steps interactions, where you need to explore an environment and talk to multiple embodied NPCs to gather relevant information. And to enable the tractable study of these complex social interactions, what we propose is to consider discrete grid worlds, which are a good compromise to feature physical and social interactions. So this social AI project is currently ongoing, but we already worked on a preliminary version. Let's have a look. So in this social AI 1.0, we started by identifying a set of important social skills to focus on when training autonomous social agents. So first, there is what we call intertwined multimodality, the ability to perform social interactions requiring to interleave different modalities of actions. So being able to move, speak, listen, and then move again, and so on, which it's trivial for humans, but really hard for DRL agents. Then there is a notion of theory of mind. So the ability to understand that there are social peers in the environment and they have their own knowledge and beliefs over the world. And finally, the ability to understand and leverage the structure of social interactions. For example, a proficient social agent should be able to detect that a social peer is trying to teach him something, and it should detect the learning content inside the prototypical verbal or non-verbal action sequence of the teacher. And we refer to these patterns of interactions as pragmatic frames. And so based on this set of social skills, we designed multiple grid world social environments with scripted NPCs and template-based language. For example, we created a coin thief environment where the agent must minimize its loss of coins by learning to give only the coins that the thief is able to see. So this requires to understand the field of view of the opponent, which is a simple form of theory of mind. And using this set of social problems, we are then able to show that a state-of-the-art DRL approach was unable to learn optimal policies in any social AI environment. And more precisely, we conducted multiple case studies showing that this DRL learner was failing due to the social complexity of our environments. And so when removing this complexity, so for example, by visually tagging coins the thief is able to see in the coin thief environment, then the agent's performance improves substantially. So that was Social AI 1.0, for which we envision many updates. For example, currently there is still a lack of structure in our environment design. We would like to better link the social problems we consider with related human or primate social experiments done in psychology. A more technical issue is that although our environments feature random objects and agent positioning to avoid trivial solutions, it's not that complex, and there is probably still a risk of seeing an agent solving some of our environments through heuristics. And so related to this, we would like to add generalization tests to make sure that agents learn general concepts that they can apply outside of the training distribution. And on a more general note, we would like to go away from seeing the social AI environments as just a benchmark with complex tasks used to check if an algorithm is better than another. Instead, we are trying to go more towards a social AI school, so to speak, which could feature a high diversity of social environments of varying complexity to enable agents to grow up to social proficiency. And to do so, we are trying to rework our environments to merge them into a larger social environment generator. And once this is dealt with, we'll then be able to use these social environments to study how to make current DRL methods able to learn social skills. And there are already interesting approaches that are being developed in the literature. For instance, in a recent article, Endus and colleagues presented an auxiliary predictive loss that when combined in a classical DRL architecture could lead to the emergence of imitation abilities. More precisely, as shown in this video, their learning agent, whose view is highlighted in red, learns to follow experts in a discrete checkpoint tracing environment. And so their approach looks quite promising, and it would be interesting to see if it could be applied to more complex forms of imitation. Here it's just about following experts by being right behind them. And obviously, regardless of how the social DRL agent is engineered, it would be quite interesting to see how ACL methods could help in controlling its training session over the procedural social environments. So to be continued. All right, now let's conclude and discuss about interesting next steps related to this thesis. So this work focused on the challenge of improving the abilities of current machine learning models through an environmental perspective. As such, we focused mainly on the study of automatic curriculum learning methods able to control the evolution of environment presented to a given learner. And in our last project, we also emphasized the importance to design the right kind of environment, and we argued that they need to be more social. In a forthcoming one-year postdoctoral project, which should start in March, we would like to continue to study how ACL algorithms can be applied for generalization beyond the set of teaching situations considered during the thesis. For example, we would like to see how it scales when used for bigger DRL models, trained to learn policies from pixels in complex procedurally generated environments. And a perfect testbed for this is the ProgGen benchmark, which is being increasingly used to study generalization and features a large set of Atari-like procedural environments. The first challenge here, however, is that the current version of ProgGen was not designed to study teacher algorithms. And so they did not make the procedural level generation accessible and controllable. So our first step will be to get into their code base and change that. And once this is dealt with, at least on a few of their environments, we'll be able to see how LPGMM and our other teachers in TeachMyAgent are able to deal with these new task spaces. We checked a few of them, and it seems like they are quite high dimensional and can have both discrete and continuous dimensions. And also something we'd like to study is how ACL might be combined with existing architectural biases targeting generalization. For example, could we use ACL both to control the procedural generation, but also to schedule data augmentation mechanisms? And in the long term, another subject we would like to study is the design of teacher algorithms able to iteratively construct procedural tasks. So the teacher is no longer sampling from a predefined task space. It is a builder policy that assembles an environment step by step. An important milestone in that direction is the paired algorithm from Denis and colleagues. So in a recent paper, they show that their approach is able to iteratively construct mazes of appropriate difficulty by choosing where to put the agent, the goal, and then obstacles around the map. And as you can see on the video, this leads to quite complex mazes. So it opens up interesting perspectives. For example, could we scale this approach to more complex procedural worlds? As so far, the discrete maze builder environment is quite limited. And more generally, an interesting question is, how could we leverage the learning progress-based teaching mechanisms we studied in this thesis and apply them in such iterative task building scenarios? And so here, one important question is how to efficiently estimate learning progress when the difficulty of the environment might actually come from a single step in the iterative building process. And by the way, making progress in that realm could also impact related problems, such as learning teacher algorithms able to create compositional tasks from primitive subtasks. For example, this has recently been done in a paper from Gur and colleagues, where they used an ACL system similar to paired and applied it to guide the learning of a DRL agent, learning to fill online forms. So finally, an agent able to withstand online administrative mazes. All right, so before closing this presentation, I'd like to quickly mention an ongoing side project in which I'm participating. So a quite expressive compositional space on which one could apply ACL is language. And currently, a popular topic around language are works using deep learning architectures called transformers to learn language models. And so multiple work showed that when trained on large text databases, these language models could then be leveraged to perform various textual tasks, such as question answering, calculus, summarizing texts, and so on. And recently, a few works started to consider how to use handmade curriculum learning methods to train these language models. And so inspired by these, we are trying to see how we could apply the teacher methods we developed in the thesis to this setting. So we did not obtain significant results yet, but this project raises interesting questions, like how do we map text documents into a task space? And do we even work at the level of document or learning batches or text blocks? And so given this is decided, how do you map these samples into a coherent task space? All right, I'll close this parenthesis here and finish the presentation by acknowledging the many people that participated in the research projects done during this thesis. Nothing would have been possible without my supervisor and co-authors. Finally, I'd like to thank again all members of the jury for the time they spent on my manuscript and now on this presentation. And that's it.